Y4E Gauss Law. We first consider electric flux. If an electric field is present, we have a surface as a simplest case, a flat surface. An electric field passes through that surface with an angle, the perpendicular direction. If the surface is parallel, the electric field does not penetrate the plate, so we do not consider this case. That means the flux passing through this surface is zero when it is perpendicular. And if you rotate this surface to make it a right angle, then the flux is simply defined by the electric field, the constant electric field, multiplied by the area of the surface. In general, the electric field and the normal vector and hat of the surface can make an angle because it is the case when the electric field and normal vector of the surface are parallel, theta equals 0, so we can consider the scalar product to compute the electric field flux passing through an infinitesimally small patch whose area is this sigma and the normal direction is n hat, so that the surface element vector is a product of the area multiplied by normal vector. In that case, electric field flux is just a scalar product of the electric field and small patch vector. The magnitude, the value is just a product of the electric strength of the electric field and area of that surface and multiplied by the cosine theta, where theta is the angle between this normal vector and the electric field. Electric field can vary depending on the position because the field is a function of position. And we have a surface. Sometimes we might have a curved surface. How can I compute the electric field flux passing through the surface? We divide this one into small patches. This patch has its own normal vector and area of the sigma. We sum these contribution by evaluating the scalar product with the electric field at every point. E, electric field, the scalar product with the small patch area vector, sum them all. Sometimes we use a special notation for the surface integral when the surface is not open but closed. Closed means we have a volume, simply connected volume, that does not have any cavity in it, a filled space. Then the boundary of this volume is a closed surface. For example, spherical surface is a closed surface enclosing a ball. So we denote this closed, the integral over the closed surface. We put a circle on it. Electric field flux due to a point charge can be evaluated in the following way. We consider a charge Q placed at the origin. Then the electric field at any point is expressed in terms of due to the Coulomb's law. Electric field flux can be computed by computing the scalar product of electric field and area vector. Previously, we learned how to parameterize the spherical surface of radius r centered at the origin. We have introduced the z-axis, the angle theta, polar angle theta that runs from 0 to pi, and azimuthal angle about z-axis that has been measured from the x-axis by angle phi. Phi runs from 0 to 2 pi. Okay, then the area of this spherical surface is r squared multiplied by the solid angle. And the solid angle is the integral of the cosine theta, where cosine theta runs from -1 to 1, and azimuthal angle. As a result, 2 times 2 pi was 4 pi. So the area of the surface is 4 pi r squared. So in here, the electric flux is the electric field, scalar product of the electric field and infinitesimal area vector. And if we copy this one in here and use the fact that this sigma in here is parallel to the radial vector. The radial vector in a polar coordinate system was E3 cosine, E1 sine theta cosine phi, E2 sine theta sine phi. This was the unit radial vector in the spherical polar coordinate system, and the area vector, infinitesimal area vector, and the direction of the electric field, they are parallel. Therefore, this scalar product gives just ER hat dot ER hat. That is exactly 1. That's the reason why the overall vector for the electric field, the strength of the electric field, and just the area of a patch is shown in here. Because the area of the patch is just the area of the spherical surface of radius r. It is 4 pi r squared. 4 pi cancels, and r squared cancels. And what you really find is just charge over permittivity of the vacuum. This is called Gauss law. Let us consider the differential form of Gauss law by making use of divergence theorem. Gauss law relates the net flux phi. We have a subscript in here, electric flux. Later, we will also consider magnetic flux when we consider the Faraday's law. Phi penetrating a surface, especially a closed surface. This notation indicates that this closed surface encloses a volume V. Due to the net electric charge, the subscript enclosed means the charge contained inside the closed surface. By making use of the divergence theorem, we can express the electric flux. Electric flux is like that, surface integral. But we know how to convert this one as a volume integral. And is this as mathematical identity we have proved, and later we will consider in this semester again. But anyway, right now, forget about the details of the derivation. Just copy the result for this identity. The electric field flux integrated over a closed path is nothing but the volume integral of the divergence. What is the divergence? X derivative of the X component of the electric field and Y derivative of Y component of the electric field and Z component, Z derivative of the Z component of the electric field. That's it. So electric field can be computed by taking the minus gradient. You remember the conservative force is always expressed as a minus gradient of potential energy, and we divide this one by the test charge, then this one becomes the electric field, and this one becomes electrostatic potential. This U represents the electrostatic potential energy, and if we scale by the test charge, then we end up with the electrostatic potential. So minus the gradient of potential, V is the potential. Okay, we shall find that electrostatic potential is this. Even though we did not learn in detail about the electrostatic potential, however, we know very well about the gravitational potential because both the gravitational force and the electrostatic force are governed by the inverse scale law. The only difference between the two forces are the coefficients. 1 over 4 pi epsilon 0. But in the gravity, we have minus capital G. And we have the product of the electric charges to compute the Coulomb's law. For in the case of Newtonian universal gravity, the strength is multiplied by the product of the masses of the two particles. Anyway, the geometric dependence that is 1 over r for the potential is identical. That must be identical to each other. All right. Then we can evaluate the divergence of the electric field. Divergence of electric field can be made because this is a charge distribution. I don't expect too much difficulty to compute this, but it is more or less out of the scope of our class. Just forget about the detail, but follow the result. There is an identity. This identity, this is a Dirac delta function, and electric field flux, by definition, this and then use the divergence theorem, we find this. And according to the electric field expressed in terms of minus gradient potential, and the potential is this, and we end up with the fact that we have a 1 over r square style in it. This 1 over r square style will give, that is by making use of the identity, what we have is a Dirac delta function. It looks very complicated, but this integral is very trivial. The result is, after integrating over x prime, the Dirac delta function replaces the argument x prime as x. That's it. So, at the end of the day, you will find that electric field flux passing through a closed surface that encloses a volume V is nothing but the volume integral of the charge density. What's that? Charge density's volume integral is the net charge enclosed by the closed surface S. That is the net charge inside the volume. This is the integral form of the Gauss law. Integral form of the Gauss law states that electric field flux integrated over a closed surface is the charge contained inside this closed surface divided by epsilon 0. And actually, this integral can be shrunken into a very tiny region. In that case, we can find that this volume integral is a divergence electric field volume integral. This right-hand side is a volume integral of charge density divided by epsilon 0. Okay. Let's shrink this one into a very tiny region. Then the integrand is frozen into a constant function. In that case, we will find that both integrands should be the same. That is called the corresponding differential form of the Gauss law. And actually, this is Maxwell's equation representing the Gauss law. Gaussian surface. Gaussian surface is a closed surface to compute the electric field flux. Gauss law relates the electric field on a Gaussian surface that should be always closed, and it must enclose volume V, and that contains the net charge Q inside that volume. The area, by the way, this kind of detailed explanation can be understood much easily when we simply apply the method to compute the electric field, not by making use of the definition of the electric field by integration as we have done in Y3, but by making use of some symmetries of the system. Let's see, there is a charged plate. Charged plate is charged with some charge density sigma. If it is uniform, there is no way to have the electric field that is not perpendicular to this plate because of the symmetry. Up and down, right and left, there should be cancelled, and we must end up with the electric field that is a normal to the plane. If it is positive, it should be in this way. If the charge density is negative, In that case, on the other way. Anyway, we have chosen a very tiny cylinder, a symmetric cylinder. And let's see the electric field penetrate in both directions, but this side there is no electric field penetrating the surface called B. So what we have to consider is the electric field passing through this side A and the other side called C. We know the electric field must be in this way, and because this distribution is uniform, the magnitude of the electric field must be E0 in both directions. Then the flux passing through this with the cross-sectional area A is AE0 to the right-hand side, and the other side, because of the symmetry, this integral should give this. And what is the amount of charge? This charge is sigma times A, because the sigma is the charge density per unit area, and A is the area. A cancels. And flux, because of the Gauss law, net charge must be divided by epsilon zero. A cancels, and we have 2E0. Therefore, E0 is sigma over 2 epsilon 0. That's the reason why the electric field just in front of a uniformly charged infinite plate should be along this direction. If sigma is a positive and magnitude of the electric field is sigma over 2 epsilon 0 in either direction. So next we consider a cylindrical symmetry. We have a uniform charge distribution with the charge density lambda is a Q over L, something like that. And here we have H. Let's rewrite this. Q over H is lambda. What happens to this case? Because of the symmetry, electric field has a component along the planar radius direction only. It is impossible to have the direction along the z-axis. And at any point, the electric field must be directed from the center. And this line must be perpendicular to the wire. All right. Then, unlike the case what we have done with the integral, we have a Gauss law. What should I do? Gauss law states that electric field penetrate this direction and unfold this side, and we have a H and radius of rho, and this is a 2 pi rho, and every point the direction of the electric field and the direction of the surface area of a small patch must be parallel. And area A is 2 pi rho H. And this area, so 2 pi rho H, and the electric field, this product is the integral. And what happens to these two base? It's a 0 because the electric field does not have a contribution normal to this plane. So what we have done is enough. This is a whole electric flux. And what is the flux? According to Gauss law, net charge divided by epsilon zero. What is the net charge? Lambda multiplied by h is the charge enclosed by this cylinder. As a result, h cancels and the final result is lambda over 2 pi epsilon 0 rho. We can see in two dimensions, even though it is a three-dimensional problem, we have one dimension along the z-axis has been discarded. It has shrunken, reduced into just a two-dimensional problem. So in that case, it does not follow the inverse square law. In 2B correspondent for the 3D inverse square law is just 1 over rho. It is an inverse law for the cylindrically symmetric problem. During these kind of calculation, you are frequently to convert a Cartesian integral that is a little bit awkward to evaluate into an integral in terms of the spherical polar coordinates or two-dimensional cylindrical coordinate system. When you convert the integral expressed in terms of Cartesian coordinates into curvilinear coordinates such as the cylindrical coordinate system or spherical coordinate system, you should be very careful with the Jacobian. Jacobian makes the volume expressed in a single coordinate system. For example, Cartesian coordinate system is very convenient to express the volume of a cube. However, it is inconvenient to parameterize the volume of sphere, for example, or disk. In that case, it is very good to use the two-dimensional polar coordinates or three-dimensional polar coordinates. However, even though only the radius has a correct dimension of length, phi and theta, they are not the coordinate with the dimension of length. We have missed two dimensions in here, and that missing dimensions of length squared must be included in the Jacobian to make these two integrals to be the same. They are called Jacobian. And if you look for some useful formulas driven in this paper, perhaps it is a very nice chance to study what the derived delta function is. Okay, anyway, in X, we have already studied how to evaluate those Jacobian. That's it.